In this video, we are going to finally take that major step, having looked at integrals in various forms and what they might mean. How do we actually compute the value of them in the general case, as much as we can? The recipe for how to calculate the value of an integral is through the fundamental theorem of calculus, which is obviously one of the major building blocks of this course. If we have an integral and we want to get a value for it, how do we go about doing that? Here's the recipe. If we have the integrand, f of x, if from there we can build a related function called capital F in most textbooks, where f prime of x, of the big F, is equal to the original integrand, then we can calculate the integral value simply by subbing in the bounds of the integral into this mysterious big F of x function. Plug in the upper limit, plug in the lower limit, and literally subtract. So this is hard and conceptual. We built integrals by looking at scenarios, by looking at examples. We can build integrals that would represent a quantity we care about. This is super easy. This is plug a number in, plug another number in, and subtract. If we can find this mysterious f of x, this capital F of x. So that is going to turn out to be our new game. Now what is this capital F of x here? Well, here is what I like to think of as the cycle. We have big F of x. If we take a derivative of that, then we get to our integrand. If we go backwards, that is what we're doing when we're integrating. We're starting this time with little f of x and trying to find big F of x. And one of the ways we can describe that is taking what we've been given in the problem. This is what we know. We want to find this other thing. We're undoing the differentiation process, or we're finding an antiderivative. That is why this is the fundamental theorem of calculus, is because it relates what we were doing already, derivatives, to what we want to do now, which is evaluate integrals, and it turns out it's just the opposite process of taking derivatives. So, fundamental for a very good reason. It's tying two of the most important pillars of calculus together. To paraphrase that here, what we're doing is looking at our area calculations and relating it back to what we did with slopes, but it's changing the direction of the process. Earlier, we had functions and we found the slope by taking the derivative. Now we have a function and we want to find the area. We're going to do that by taking the antiderivative, or the inverse of the derivative, in our process and our calculations. In other words, if we can find an antiderivative of the function in our integrand, then we get that last easy step. So we can compute an area very easily, much more easily than the left sums, right sums, trapezoid rule, all those other things, and we get an exact value back. Well, if it's so easy, let's see where the complications arise. We will do that through a series of examples where we build from simpler to more complicated integrands and see what kind of issues arise.